So, good afternoon, everyone. I'm on minimum brightness there. Welcome back to Math 122. So today we're going to talk over sections 1.8 and 1.9. And we really are going to get through both because I've decided that we're going to learn less, meaning that we're going to skip a little bit of material here that we won't skip it, we'll talk about it, but we won't go in super detail because I don't feel like it's that important, to be honest, and you should have learned it in pre-calculus. And in any case, it's not really going to come up for the rest of this semester, so we're going to talk about it briefly and then move on. But if you want to talk about it in greater detail, then it would be best to send me an email so that we can set up a private meeting, or I can find a time when we can talk during office hours or something like that. Okay, so regarding your homework, you have 1.7 is due tomorrow, and your next quiz is going to be this Thursday. You're probably noticing at this point there's always a quiz on Thursday, and I thought I would clear up how the quiz content is determined. So the quiz content for a given quiz, it will cover the material from all of the homeworks that were due between the last quiz and the next quiz. Okay, so for example, the last quiz was on 1.4 and 1.5, so we had homework 1.4 and then homework 1.5, right? And then we had a quiz, and then we have homework 1.6, and then we have homework 1.7, and then we have a quiz. So the quiz this week will be over whatever homeworks were due in between the last quiz and the current quiz. So that's going to be this week, it's going to be 1.6 and 1.7. So that way you can always know what's going to be on the quiz without even me telling you in class. So that's the quiz. Okay, my office hours are the same as always. Okay, 11:30 to 1 on Thursdays, Wednesday from 3 to 4. It's a great time to study for the quiz since you know that the quiz questions come directly from the homework. You can study all the homework questions with me during office hours. Okay, and we'll go over all of them. And then if you can't go to office hours, then go to the Math Tutoring Center. I'm in there from 10 to 12 on Tuesdays, and other graduate students are there from like 10 to 4. SI sessions, as always, are here. I'm beginning to sound like a broken record, but seriously, if you feel like you're starting to fall behind, the number one best thing that you can do for yourself is to make use of either office hours, Math Tutoring Center, and SI, because it's really hard to learn math on your own, because not only do you not know things, you don't know what it is that you don't know, or you don't know what it is that you're having a misunderstanding about. And so if you can have somebody there like assessing you and determining that for you, it takes a lot of the guesswork out. What I like to say is, look, 1 hour in office hours with me is worth 4 hours of studying on your own. That's what I say. 1 hour in the Math Tutoring Center with somebody else, maybe that's worth like 2 hours of studying on your own. But it's still better than studying on your own. So please, 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 please use those resources if you need them.
So you're going to be this side?
Sorry?
You're going to be in this side? Are you going to be there?
At the SI?
Yeah.
No, that's Jacob. So Jacob, you took the class, what, last semester or the semester before?
Yeah, last semester.
Okay, so Jacob took the class last semester and got a good grade and knows what's up with the class, so he'll help you with your homework as well, okay? Good question. Any other questions? Are you Allie? Can we talk after class? Thanks. Okay, so just because I tried to send you an email, but like something's wrong with the email system. Oh, you got it? Okay, gotcha. All right, well, let's still chat. Any administrative questions before we start in on content for today? All right, doesn't seem like there are, so I'm going to go over what we talked about last time, and then for today's class, I'm honestly going to motor mouth for a little while, and then what I'm going to do is, as time allows, I'm going to go back to examples and we'll do a bunch of group work at the end. Okay, so it's going to be a lot of me talking and then group work, because I don't know how to pace it properly to get through all this stuff today. So let's talk about what we talked about last time. which was more exponential functions. Okay, we had finished logs already, right? Oh, yes. So we learned about how to solve equations using logs. Okay, and the way that we solve equations using logs is when we have the thing that we want in the exponent, we have to use the logarithm and the associated rule that says ln of a to the p is equal to p times ln of a. We use this associated rule to solve equations using logarithms because it allows us to take the unknown quantity out of the exponent and down onto the base level. From there, we can just solve it using our usual algebra tricks. Okay, so that's the purpose of logarithms. Then we talked about converting between the two different types of exponential forms. Those types are the annual form of the equation and then the, quote, continuous form of the equation. Okay, so anytime that we talk about continuous interest or anytime we talk about radioactive decay, usually we're going to be using the right-hand side equation. And then sometimes if we're talking about like annual interest or something like that, then we'll use this, or sometimes population. You can use either one that you want for either, you can use either equation that you want for any exponential growth or decay problem. It's just really a matter of perspective, and that perspective in terms of the textbook and in terms of the way things are written in the mathematical literature is sort of affected by what people have traditionally used. Okay, so people have traditionally used this exponential model to model exponential decay of radioactive isotopes and that sort of thing. Doesn't mean you can't use this one, okay? So that's exponential forms. We learned how to translate between them, which amounted to using one of these two equations, right? If you know what A is, you can figure out what K is by taking the natural log. And if you know what K is, you can figure out what A is by doing e to the K. Okay, so that's all that there was to that. I think that's where we stopped. So any questions on what we talked about last time before we talk about new stuff? Yeah, Alex.
I feel like the homework had there was like one question I just like did not have the money to do, so like I looked it up.
Is it about the doubling time in HalfLife? Well, what was the question about?
It was just like I knew how to do it because I did in high school. I just didn't like I just had to like refresh my memory. It was like the 5e squared to 5t equals 9e squared to 4t.
Why don't we talk about it together? You said 5e squared to the 4t?
No, 5e raised to the 5. Right. 5e raised to 5t equals 9e raised to 4t.
Okay.
Yeah, it was just a little sus.
All right. Extremely sus equation right here. Well, let's see if we can solve it.
I didn't have an example to reference from class.
No, that's okay. You're right. We haven't solved an equation like this, but I claim that we have seen the tools that you need to solve it. And let me show you. Here's what we can do. I can divide both sides by 5. Nothing crazy, right? And then I can divide both sides by this guy. Do you agree? To get...
I didn't take this route, but...
Okay. Well, you could do it in many different ways, but this is maybe the easiest way to do it.
Yeah, looks like it.
Equals 9/5. Okay, and now, Alex, you tell me what I'm going to do on the left-hand side.
It comes out to e raised to t.
Yeah. If I have e to the something divided by e to the something else, we combine the powers by subtraction. 5t minus 4t. And then e to the t equals 9/5. And then natural log. And what happens on the left side when we do natural log of e to the t?
Cancel
it just gets t. And then we get ln of 9/5 on this side, and then ln of 9/5 on that side. Okay? So just takes a little bit of moving stuff around, you know, and seeing what you can combine. And maybe the first sort of giveaway that this is a good route to take is thinking like, well, I kind of don't like that my unknown is in two places, right? I'd rather my unknown be sort of all combined into one. So, you know, if you wanted to, you could also say, well, I'm going to take the natural log of both sides right away or something like that. And then I'm going to, well, would that work? Yeah, I suppose that would work. You could do something, okay, let me show you one other way you could solve this. That's probably the easiest way.
Can I try?
Yeah.
Alright.
Go ahead.
Let's write the equation first.
Well, it's already right, it's right here.
Damn.
ln parentheses 5e raised to 5t parentheses equals ln parentheses 9e raised to 4t parentheses, and then you use the natural log rule where you separate the 5 from the e raised to 5t. So it's ln parentheses 5 parentheses.
And then a plus, right?
Yeah, plus ln parentheses e raised to 5t equals, and then basically the same thing on the other side.
Yeah, okay, I'm going to finish it from here.
Oh. That was me even twice.
Sorry.
Okay. So now.
I can't walk and chew gum.
So now you get the e's on the same side and the ln's on the other. The e raised to the 5t. Nope. The e raised to the 14 needs to go to the other side, and then the ln.
Yes, but I'd argue that we can make this simpler here by doing the following. ln of e to the something is just that thing, right? These two undo one another. So this is just 5t. And this is just 4t, right?
I just didn't get to that point yet. I was mad at that.
Okay. But then, yes, you move the logs over and move the t over. You get t equals to ln of 9 minus ln of 5. Why did we get a different result than what we got down here?
Because when you put it in your calculator, you get the same numbers.
Yes, but also, these two things are the same, aren't they? ln of something divided by something, there's a log rule which says you can break that up using subtraction. Okay? All right, so thanks for that diversion, Alex. I appreciate that. No, I'm kidding. What I like about this is, okay, first of all, it's good that you are all engaged in your own learning, and it's also good to see that, look, mathematics is mathematics. I am not the kind of instructor who's going to sit here and tell you, oh, well, you have to do it my way. If you do it in a valid and correct way, then good for you. Okay, so this is just goes to show you, look, there's more than one way to skin a cat. Not that we would ever do such an inhumane thing. Okay, so any questions on this example before we move on to new material?
An analogy from skin cat. Never heard of that.
I don't know, maybe back in the day they were doing such treacherous things. But it's best not to think about it. Let's move on and think about more different math. Okay, so what else did I want to talk about? Oh, yes. So I wanted to talk about So we did talk about annual interest rate versus continuous interest rate. It's the same as what we just talked about. Difference between e to the k and difference between a. And then what I wanted to talk about, the final thing from 1.7 is half-life and doubling time. Okay, half-life and doubling time. And the interesting thing about exponential functions, okay, which describe things like population growth or the growth of your money in the bank or radioactive decay of a substance, okay, is that the half-life and the doubling time, which are, spoiler alert, the amount of time until 1/2 of the original substance or original quantity is left. So this is only for decay, obviously. And then for growth, we want to know how long does it take for us to have twice what we started with. So this is doubling time, so this is for growth. And that's, okay, the amount of time until what? We have twice the original, 2 times the original quantity. Okay, so the interesting thing about this is that it doesn't depend on how much we start with. Okay? 1 kilogram of a substance is going to decay to half a kilogram in the same amount of time that it takes for 1 ton of a substance to decay to half a ton of the same substance. Right? That's because, look, the more particles there are in the original quantity, right? The more particles there are, the more decay there is, okay? Or you can make it simpler than that, right? You can think about population dynamics, right? If you have like a population of yeast, or even a population of humans, right? The more humans there are, the more things are happening which are making babies, right? So the more humans we have, the more babies we get, and the more humans we have, and the whole thing just like spirals out of control, and that's why we've like destroyed the planet, right? Okay, so let's see how it works mathematically. So what we want to do is find the time t such that, okay, and let's recall that, let's say that we're going to use p of t, we'll use p of t equals a, sorry, not a, but p naught a to the t for this example, okay? Then what do we want to see? What we want to know is, well, how much time does it take for us to have half of our original quantity? Well, our original quantity is p naught. So if I plug in t1/2 to the function, okay, t1/2, well, you could write this as p naught times a to the power t, 1/2. Okay, a little hard to see that. Let me write that better. t1/2 is equal to, well, how much should we have left after we wait for this much time? Well, we started with p naught, and this is the half-life, so we should have half of what we started with, which could be written as 1/2 times p naught. Okay? So you wait for a certain amount of time, then later your original amount has decayed to 1/2 of that original amount. And you immediately see why this is not going to have anything to do with what our original amount is. Why does this not have to do with what our original amount is based on this equation? In other words, why is p0 irrelevant to finding t1/2? Yeah, Aiden.
You can cancel it out.
Yeah, because you can cancel it on both sides. Divide both sides by p naught, and we attain the equation a to the t1/2 equals to 1/2. And then to find t1/2, t1/2 is in the exponent. How am I going to get it out? Using natural logs. So ln t1/2 times ln of a is equal to ln of 1/2. And subsequently, you can divide both sides by ln of a to get t1/2 equals to ln of 1/2 divided by ln of a. So let me maybe move this down a little bit so it's a bit clearer. Okay, so this is just how you can find the half-life. So if you want, you can memorize this formula, okay? And it will tell you what is the half-life after, or what is the time needed to attain the half-life. But what I would recommend instead is remember that if you plug T1 half in, you should have half of what you started with, which is easily represented by the expression 1/2 times P naught, because P naught is what we started with. 1/2 of P naught is half of whatever we started with. And we know it doesn't matter what we start with. Okay, so you can do this without knowing what the original amount is. Okay, questions on half-life? Okay, well, we have a similar concept for exponential growth. We call it doubling time. It's the amount of time it takes for the human population to grow from 1 million to 2 million, or 1 billion to 2 billion, or your money in the bank to grow from 1,000 to 2,000, or something like this, right? So this is the doubling time. So if I plug in the doubling time into the function, I get P naught times a to the T2. And then, of course, this should be equal to what? If I have twice what I started with, what am I going to put in this blank?
2 times P naught.
Yeah, 2 times P naught. And then again, cancel, cancel. Okay. Dot, dot, dot. Do some algebra. T2 equals ln of 2 divided by ln of a. Okay, the algebra is exactly the same as the previous step. Okay, so that's how we find half-life and doubling time. Any questions on either of those two concepts before we move on to the next section? Okay, if we have time at the end of class, we'll come back and do some examples of problems with that. Okay, so I'm going to skip ahead a little bit to section 1.8. Okay, and section 1.8 is about combining functions in various ways. Okay, and the most important, probably for this class, regards compositions of functions in terms of plugging one function into another function. Okay, so we call this composition, or the way we read this is we can read this as f of g of t. Okay, that's one way. Or you could say f composed with g of t, or something like that. Okay? So this is how we read this out loud. Okay, and what does it say? Well, we're just going to take t, and we're going to use PEMDAS. And remember, PEMDAS, the P stands for parentheses, meaning that we start on the innermost part, right? So we're going to take our t, we're going to plug it into the g function, we're going to see what we get. And then we're going to take whatever we get, and we're going to plug it into the f function. And then we'll be done. Okay, so this is the way that a composition works. Start from the inside, work to the outside. Okay, so we're going to talk about two different things. We're going to talk about evaluating them, and we're going to talk about finding a formula. Okay, and I'm going to do that through a couple examples. So, okay, let's start with plugging first. Let's start with plugging first. Okay, so given this table of values, we want to find g of f of 6, f of g of 2, and all this business. Okay, so what are we really doing here? Well, again, I said we're going to start from the inside and work our way out. Okay, so the first thing I'm supposed to do is just kind of ignore this g for the time being. All I want to do is write inside of these parentheses whatever f of 6 is. Okay, I want to write whatever f of 6 is. So the first thing I do is I start with 6. I go to the table and I look for the input being 6. Here it is. And I'm going to look for the output when x is 6. So now I'm going to go to the output, but I'm going to go to the output for the f function because that's the one I'm applying first. And that's 3. Okay, so f of 6 is 3. So since f of 6 is 3, I'm going to replace f of 6 by the thing that it is equal to, and I get g of 3. Now what am I going to do?
Find the output of g of 3.
Yeah, by taking 3. So should I go to where f of x is 3 and then find g like here? No, what do I do? 3 is the input here, which means I need to go to the x row and find 3 in the x row. And then I need to map that down to what is g when the input is 3, which is 10. Okay, so we get 10. So the whole process looks kind of like this. We start at 6, we went to 3, right? And then we went from 3 to here, and then we went from 3 to here, okay? So the whole process was like starting here, and then to here, and then to here, going like so, okay? All right, and we can also do f of g of 2. That's fine. We just start with g this time, okay? So we go 2. Now we're going to go to what is the output of g. When x is 2, it's 2. So we get f of 2, because g of 2 is 2. And now we just plug in 2 into the f function, and we get -4, etc. Right? It's no problem at all for us to plug one function into itself either, right? What is g of 6? G of 6 is 2, so this is just g of 2. And then what is g of 2? G of 2 is 2. So we get 2. Okay? Any questions on composing functions in terms of plugging here? We're just plugging into the first and then plugging into the second. From the inside to the outside. Okay, then let's see how we find a formula for a composition of functions. Okay, how we find a formula. Well, all we're going to do when we do a formula here is just like before, okay? How do I do like f of 2 if f of x is x squared? What I do is I take the x and I replace it by 2, right? That's all I do. I replace the x by 2. When I do f of x plus 1, what am I going to do? I'm going to take the function x squared and I'm going to replace the x by whatever's inside those parentheses, which in this case is x plus 1. So in this case, it would look like f of x plus 1 would be, I'm going to replace the x with x plus 1, except I'm always going to, what's PWP stand for? You remember that one? Have I done that one yet? Okay, I thought I did that one, but maybe not. PWP, that's plug with parentheses. Always plug with parentheses. So wherever I see an x, I'm going to replace that by whatever's in here with the parentheses, okay? The reason I need to do that is because I still need to square all this jazz. Well, that's easy, right? All I have to do is make it x squared plus 1 squared, right? Which would just be x squared plus 1. Uh-oh. I made a mistake. Someone help. What did I do wrong? Yeah, no.
There's 2 sets of whatever's in the parentheses, so you gotta like make 2 different sets of it and then multiply them and distribute onto each other.
Yes. It's very easy to make this mistake. Okay, very easy to make this mistake and just think, well, we can just distribute, right? But powers don't distribute this way, and let me show you why. What is squaring something? Squaring something is just multiplying it times itself. So x plus 1 squared is the same thing as x plus 1 times x plus 1. If I multiply two things like this, what do I have to do?
Foil.
Foil, right? Foil, first, outside, inside, last. So that's x squared plus x plus 1 squared, which is x squared plus 2x plus 1. So if we had just gotten this, we would have been totally missing this middle term here, okay? So we got to remember that we can't distribute powers like that, all right? Okay. So that's how we plug one function into another. Any questions? Okay, then yeah, okay. Let's move on to graph transformations. And I'm going to go through this very quickly because graph transformations is a big part of 115, is a big part of pretty much any high school curriculum. And also, we're not really going to use graph transformations very much in this class. So if you remember them, great. If not, please come and talk to me during office hours or when the need arises. So what is the graph of a times f of x, or f of a times x, or f of x plus a? Well, all of this stuff is going to look like the graph of f of x. It'll be the graph of f of x, but ... Now we're going to fill in the but what. Okay, it's going to be the graph of f of x, but if we multiply by a number a, if a is larger than 1, stretch vertically by a. Or if a is less than 1, we are going to shrink or compress vertically by a. Okay, what I mean by that, okay, is the following. If I were to grab, okay, up here, remember where this dot is. If I were to grab, let me just move it down. Actually, maybe I can just do this. No, I can't, because it scales it properly. Okay, if I were to grab right here on like Microsoft Word and shrink it like this, right? That's a vertical stretch, or shrink. There's a vertical shrink if I push it like this. But if I stretch it like that, that's okay, vertical stretch. So that's what's going to happen to the graph, okay? Likewise, for f of a times x, well, it's on the inside. And the trick to understanding transformations is to understand that when we do something on the outside, it's got to do with the world of up and down. And when we do something on the inside, it's got to do with the world of left and right. Okay? So if a is larger than 1, we're going to shrink horizontally by a. And if a is less than 1, we're going to stretch horizontally by a. F of x plus a, what happens if I add something on the inside? Does it have to do with the up and down world or the left and right world?
Left and right.
Left and right, okay? And this is going to be not a stretch, actually, but a shift. Okay, a shift. If a is positive, actually the better way to say it is to say you shift a units to the left. Okay, to the left. It's a little bit weird. You think positive, you think maybe we're going to the right. But actually you got to remember when we're on the inside, okay, things are weird, right? When a is bigger than 1, we get a shrink. What? When a is positive, we move to the left. What? Well, you just need to remember that it's sort of the reverse of what you might imagine otherwise. Okay, so if a is negative, of course, shifting negative units to the left is the same as moving to the right. Okay, same as moving to the right. All right, last three. If we add on the outside, we shift up a units. So if a is negative, we go down, namely. Negative x on the inside, reflection about the y-axis. That is a horizontal reflection. Negative on the outside, reflection about the x-axis, or a vertical reflection. Okay, so I know I went through these really fast, okay? So what I'd like for you to do is, if you need the review for this, I want you to go to the notes, okay, and check some of these problems down here, okay, and practice with them. But I'm going to show you one really quickly of a mix and match, okay, where we can see the effect of these different kind of transformations, okay? So let's just start with A. So my original function looks like an absolute value type of function here, and we're just going to do various different transformations. So the first one says, okay, just plus 1 on the outside. If it's on the outside, it's got to do with the up and down world, right? So plus 1 is going to move us what? 1 unit up, okay? 1 unit up. So I'm just going to take this whole thing and I'm going to move it 1 unit up. So that would look kind of like this. Yeah, kind of like this. That's what it would look like. So that looks like I to me. Okay, next up is B. We move what? The 3 outside means go up 3. What about the minus 1 inside? Move to the right 1. So right 1 and up 3 looks like V. Or 5. Okay, so C. We already did this one basically. Minus 2 on the inside, that's 2 to the right. So that would be I. Okay, plus 2 on the inside, what's that do?
Left 2.
Left 2. And minus 3 on the outside, what does that do? Down 3. Okay, so over left 2, down 3. That puts us as 6. Okay, and then what do we got? Minus 1. Come on, we can do this. IV, so this is just going down 1, right? Goes down 1 unit. Or this one is just to the left 2 units. So that would be II. Or 2. Okay, so what is the only other thing I want to show you is, what does a stretch do? What would something like 2 times f of x look like? Well, what we're going to do is we're going to take all the heights of all of the points and double them. So this height is going to be not 1, it's going to be 2. This height here is going to be not 2, it's going to be 4, and so on and so forth. So we're going to get a picture which looks stretched like this. Okay? That's basically what is going to happen. Okay? All right. Let's have some thumbs. Thumbs up if you feel okay about graph transformations, between your previous classes and this short review. And thumbs sideways if you feel like you really wish that you had more graph transformations. Raise them nice and high for me. Okay, I'm seeing almost all up, so that's good. That's kind of what I expected. Okay, then I'm going to move on to something else. So that's all I'm going to talk about for that section. And the next section is also pretty slim, okay? I'm just going to talk about 3 more things, and then we're going to do some group work at the end of class, okay? And the three things which I'm going to talk about in section 1.9 are really just definitions, okay? There's no meat on this section at all. Okay? So, the first thing we're going to talk about is what is a power function? Okay? And specifically I want to highlight the difference between a power function and an exponential function. Okay, there is a big difference between a power function and an exponential function. So what does a power function look like? Well, our independent variable here is on the main floor. Okay, it's on the main floor. And we have some numbers being multiplied by it. Okay? We have some numbers being multiplied by it. K and P, where they're real numbers, not 0. Okay, so think things like this. F of x equals, I don't know, negative 3x squared. Or, I don't know, pi times x to the 15th. Or 1.718 x to the negative 301.5. Okay? What's the deal? We get a number and then x and then raised to a number power. Okay? Whereas, what does an exponential function look like? An exponential function, okay, why don't we call it g of x, looks like p naught times a to the x. So what is the difference? Here we have a number times x to a number. In the exponential function, we have a number times a number to the power x. Okay, so there's a huge difference between the independent variable x being inside the power versus on the main floor. Okay? All right, so just a definition. Let's see a couple examples. Okay, we got to determine whether these are power functions or not. Okay, well this one, since we can write it as x to the minus 5, I would say yes. How about b? Do we think b is a power function? Looks more like a root function to me. Let's have some thumbs. Thumbs up if we think b is going to be a power function, and thumbs down if we think maybe not. And everybody's thumbs, please. Don't be afraid of being wrong. This is a tricky one. And I'm not, don't read into my thumb. I'm just telling you to put your thumb up. Real high, please. Okay, we're pretty evenly split. Well, if I was going to write it as a power function, then I would need to be able to write it as k times x to a certain power p. Seems fairly evident that k could be like 14 or something like that. And then the question becomes, can I represent a 7th root as a power? And I think if I ask that question, people are more convinced that this maybe can be done. How can I represent the 7th root as a power? X to the 1 over 7. X to the 1 over 7. So 1/7 power is a 7th root. So this one is a power function, after all, because we can find numbers k and p, namely 14 and 17. Or sorry, 14 and 1/7, excuse me. Such that this is a power function. Okay, so you get the idea. This is a power function. What's not a power function? I don't know, maybe one of these over here. This one's not a power function. Let's see why. If we FOILed it out, we get x squared plus 3x plus 2. Okay, this cannot be written. You cannot find a k and a p such that these are equal to one another. Why? Because we have a trinomial on the left side, 3 terms. trinomial, meaning 3 names, meaning 3 terms, okay? On the right-hand side, we have a monomial, meaning 1 term, okay, with a certain power. So these cannot ever be made equal to one another. We cannot find numbers k and p such they're equal together, okay? How about c? Okay, sure. What do we think? No, what kind of function is c?
Exponential.
It's an exponential. You can tell that this is not a power function because where is the independent variable? It is not on the main floor, is it? It's in the power. That is an exponential function. Okay, so that's power functions. Questions on power functions before we see a couple more definitions? Okay, then we're going to talk about proportionality, okay, which is basically, I mean, really the only reason that I want to include this in the class is because you should, as human beings, be aware of what it means when something is proportional to something versus when it is inversely proportional to something. Because people will say this to you in, I don't know, a business meeting or something like this, or you'll hear it on the news, and it's good to understand what this means, okay? So, if something is proportional to something else, okay? Okay, so if y is proportional to x, then there exists a number k such that this relationship is true. In fact, a positive number, k should be a positive number. So what does it mean? It means you have like y equals a number times x. What kind of function is that? That's a linear function which goes through the origin with slope k, right? With slope k. So what does it mean? It means the more x you have, the more y you have. Okay? So you might say something like, my grade on the exam is proportional to how many hours I study. The more hours I study, the higher my grade on the exam, right? Something like that. Okay, this is proportional. Okay? And then we have inversely proportional, which is basically y is inversely proportional to x if there exists a number k positive such that, okay, so no one gets scared. This backwards looking e means there exists a number k larger than 0 such that y is equal to k divided by x. Now someone tell me what's going to happen to y when x gets bigger.
Smaller.
Y is going to get smaller. Okay, so when we say inversely proportional, we're just talking about a relationship where, look, the bigger that x gets, the smaller that y gets. Someone give me an example of an inversely proportional relationship.
Ice cream in the heat.
Ice cream in the heat, meaning that like the temperature of my ice cream is going to be inversely proportional to the temperature outside or something like that. Yeah, that could definitely work. Why don't we do one with my grade again, right? For proportional, I said my grade on the exam is proportional to the number of hours that I study, right? What's something quantifiable that's going to kill my exam grade?
Not studying.
not studying is not so quantifiable, though, because you can't not study. Well, I suppose you could not study for a certain amount of hours, but that's also just another way of defining how many hours that you study, right? What about something else?
Maybe sleep.
Yeah. Well, sleep, the more I sleep, okay, yeah, maybe the more I sleep, the less I study. So again, but yeah, okay, something along those lines, right? Like, I don't know. I was thinking something like number of hours that I played video games or something like that. Or, I don't know, a number of beers that I had at Jake's Yappy Hour or something like that, right? These things are going to hurt my exam grade. The more that I have of them, the lower my exam grade is going to be, okay? So that's proportional and inversely proportional. So now you'll know what that means when people say it on the news. If you didn't already, you might probably already, maybe a lot of you already know that. Okay, questions on proportionality? Yep. Such that. Yeah, ST stands for such that. Thanks for asking. Okay, so when I say there exists a number k such that, meaning I can find a number k, that if I put it in the numerator here, and I put the number of hours or whatever of x in the denominator, and I divide those two numbers, then that will tell me what is my, whatever, grade on the exam, or temperature of my ice cream, or what have you, okay? All right. So that's proportionality. And the last thing I want to talk about today, in terms of definitions, is quadratics and polynomials. Okay, quadratics and polynomials. So what the hell are they? Well, they're also different kinds of functions. So far, our library of functions that we know are linear functions. That's like mx plus b. We have exponential, which is a naught, or why don't I do p? P naught times a to the t, or p naught times e to the kt. Or, if you want, p naught times 1 plus r to the t, something like that. We've got power functions, which are k times x to the p. Now we're going to learn about two more, which are quadratic and polynomial, which you can see them here. Okay, so a quadratic q of x has the following form. It is equal to ax squared plus bx plus c, where a, b, and c, now remember, way back when we learned set notation, this means belongs to. And what does this symbol mean?
Real number.
Yeah, the set of all real numbers. And furthermore, a should be not positive, but not 0. A should not be 0. Okay, so that the leading term doesn't just cancel. Because if the leading term went away, we would have bx plus c, which what kind of function is that? Linear, right? Okay, good. So we have ax squared plus bx plus c. A is not 0. Okay, what kind of graph does a quadratic function make?
Parabola.
It makes a parabola, which looks kind of like a U shape. So if a is positive, it's going to open up. And if a is negative, then it's going to open down. Okay? So that depends on the sign of this coefficient here. Okay, the sign of that coefficient. Okay. To solve q of x equals 0, you have two methods. The first is factoring. What's the second method we can use? All right. Grouping, another form of factoring. There's one other way that we can solve quadratics using A's and B's and C's. Yeah, Erica's got it. It's the quadratic formula, okay? So the second way is quadratic formula. Which is, what? Someone remind me what it is. X equals to what? So it's negative b plus or minus the square root of what? You got it. Good. Do you remember the song? Is that how you remember it? Yeah, I don't remember the song, actually.
I didn't even know there was a song, bro.
There's a whole song. Oh, yeah.
I just, like, was told to know it. Like,
okay, so b squared minus 4ac over 2a. Okay, whatever. That's the quadratic formula. You just plug in the numbers and it gives you the answers, okay? So, okay. The other thing that I want to say about a quadratic is where is the vertex going to be? The vertex of a quadratic is always at the point negative b over 2a, comma, and how do I get the height for a certain x value? Well, you just take that number and you plug it in for x here, and well, just there and there, right? Okay, so that's all we're going to do. So we take q of negative b over 2a. Okay, that's how you can find the vertex of a parabola. Okay, which, if you open up, the vertex is also the minimum of the function. And if you open down, then the vertex is the maximum of the function. Any questions about quadratics? Okay, I know I've just been spewing a lot of definitions at you today, but I got one final one to give you, and that is for a polynomial. So what is a polynomial? A polynomial is a function of the following form. an times x to the power n plus an minus 1 times x to the n minus 1 plus dot 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 plus a2x squared plus a1x plus a0. Wow, that's a lot of nonsense. But let's break it down. All the ai, okay, an minus 1, a2, a1, a0, they're all just numbers. Okay, they're all just numbers. They're just like the a and the b and the c in the quadratic formula. Okay, they're just numbers. But the reason that I use a0, a1, a2 instead of c, b, and a is because you could feasibly have a polynomial of degree 40 where you have 40 different terms and you run out of English alphabet letters. And even at some point you'd run out of the Greek letters. And in math, there are no other letters than those two. So then we'd be really hosed. So what we do have infinitely many of is numbers, so that's why we use AI. So AI is a number, a real number, and n is an integer. By integer, I mean like dot dot dot, no. I mean 1, 2, 3, dot dot dot. So n is actually a positive integer. Okay? N is a positive integer. So let me give you an example of a polynomial. An example would be p of x equals, 17x to the 50th plus 41x cubed minus x squared plus 10x minus 1. Okay? This is a polynomial because, look, our A50 is 17, our A3 is 41, our A2 is negative 1, our A1 is 10, and our A0 is negative 1. Okay? So we have basically a sum of power functions where specifically we need these powers to be whole numbers. Okay, we need the powers to be whole numbers. Okay, so let me ask you a question. Is it true that all quadratics are polynomials? What do you think? Can you reason why? Why is a quadratic automatically a polynomial? You're right.
Is there 3 A's?
Yeah, you've got A2, A1, and A0, right? And moreover, the powers on x are all whole numbers, right? We've got 2, 1, and 0 for the powers on x. Okay, so all quadratics are automatically polynomials. Is the other way around true? Is every polynomial a quadratic? No. Someone tell me a polynomial that's not a quadratic.
X to the 5th.
X to the 5th. Just x to the 5th could be a polynomial, but not a quadratic. Because x to the 5th could be a polynomial where a5 is 1, and then you've got like plus 0x to the 4 plus 0x cubed plus da-da-da, right? Plus 0 all the other stuff. Okay, good. So what I want you to take away from this section is just to be able to identify the different types of functions. So we've got linear functions, exponential functions, power functions, quadratic functions, and polynomial functions. Those are the ones which we care about so far. Actually, that might be all that we do. No, we'll do some logarithmic functions and stuff like that. I guess we've kind of got log functions as well. Okay, so that's what I wanted to talk about from this section, is just to be able to identify them and to look at a function and say that is a linear function, or to be able to give an example of an exponential function or an example of a quadratic function. These sorts of things are crucial skills going forward. Okay, any questions on this? Yeah, Erica.
I can't so when it says functions, you can go up a little bit.
Here?
So linear exponential.
Power, and then quadratic, and then polynomial. Yeah, sorry, my handwritings leave something to be desired. Okay, then I want to do one quick group work. One quick work, everyone. And we're going to take it back to the HalfLife problems, okay? Because this is relevant for your homework. Okay, so we're going to work on problem 5 for about 10 minutes, and then we'll close for today. So work with a partner, okay? We want to figure out how much time it takes for the caffeine in a mountain condensate in my body, or in anyone else's body for that matter, to decay to half of what it was originally, okay? So we want to come up with a formula, and then we want to find the half-life of this substance, all right? So I'll be walking around to help. And I'll also pass out some of the quizzes, which are here. I just have to alphabetize them when I put them in the grade book, so we got so many B's, I never know where to put you. Christopher, Dan Weaver,
Or is it E-T?
Oh shit, I wrote the wrong number.
Nathan,
Yeah.
It's continuous, so B-E, right? Yeah.
Oh, yeah. Yeah, I'm also stupid again. Twice, one problem. Dude, no, it's impressive. Jesus. Well, that don't make no sense. 'Cause now I gotta get the A, I hate No, you got it. It's just the formula's just 55E.
So what is the formula?
Yeah, 55E014T. But I was trying to find the half-life. I didn't even realize that there was a part A of the question. I just went straight into half-life. I'm pretty sure that you can literally just do 1/2 over ln of 0.14.
Do 0.14 and do 1.14.
No, it would just be 0 because we're decaying.
Zero would it just be T? Or is it like 1?
I'll make the numbers really nice, or I'll say something like you can leave it in this form. You see what I mean? Because like you can go all the way up to here, and then I know that you know how to type that in on your calculator, right? So I just want you to know.
Okay,
Or I'll make the
half-life
numbers really nice.
equals
That does not make sense.
0.352. I don't know what that number means, but it means something.
That's time.
No, I just sauced on this problem. I can't lie to you. So it takes 0.352 hours.
Makes sense. It's 14% per hour.
I'm not here to get
I think, okay, I think it's.
I'm here to get an answer and help.
4.6 hours.
I don't feel like finding an A using this though.
One times 0.4.
Oh.
I only know this because of my bio class.
Okay, so put that in the equations.
If I do it like that,
But remember, that means leaving the body, right? So we want minus sign.
That's what I'm saying. If you had the number, if you had the number, you have to divide it out. That makes sense. Okay.
No, it's that leaving the body at a rate of 40% per hour. If it was leaving at a not a continuous rate, this is a continuous rate, but if it said nothing, it didn't say that, then it would be 85 times 8.6 to the T like this. This is how we would do it if we were using like the decimal or daily or something like that. But since we have some it just means we have changed, we gotta like this. Okay, so all we want to do is say, look, after a certain amount of time, how much do we have left? We have like 22.5. So yeah, divide both sides by 55 to get E is the 1/10, and then yeah, get this, which is this. Yeah, you're right. Yeah, you're good. Yeah, sorry.
did you get like the 4.5 just right on block?
6, yeah.
Well, not yet, but I will be.
Okay, we got 2 minutes left, so I'm going to try to really quickly wrap this one up, and then we'll close. So, okay, there's one really critical word in this word problem which is telling me what I need to do, and that is this one, the word continuous. If I am decaying continuously, then I need to use the equation P of t equals to P naught e to the kt. Okay? So, for this particular problem, P naught is going to be our original amount, which is just 55. And what's K going to be? Should we just do 0.14 t? Why not? Because this would represent growth, okay? If you try plugging in different t values, you'll notice this gets bigger and bigger and bigger over time, unlike the amount of caffeine in your body after you drink a mountain condensate. So instead, we should have a negative sign here, okay? And then what do we want to do in the second problem? Well, in the second problem, what we want is for 55 e to the minus 0.14 t, we want to find the t value such that if I plug it in here, I get half of what I started with, which would be 22.5. So to solve this, we just take it as follows. Natural log on both sides gives us minus 0.14 t equals ln of 1/2. And finally, t equals ln of 1/2 over minus 0.14. Okay, so I'm out of time. So thanks for your attention today.
I'm still like a little bit like I went through the notes and tried to like write down like some algorithms and stuff, and I got some of it, but some of it's still like it's hard to just learn just from the notes.
Yeah, it is.
Should I just come during office hours tomorrow?
Yeah, can you come? It's from 3 to 4?
Yeah, I can.
Yeah, okay. I'll see you there.
All right, I can't come on Tuesdays and Thursdays because I got biology.
Yeah, no worries, man.
All right.
Scroll up
Mhm,
to
yeah, sure.
exponential function so I can get that equation that you wrote.
Exponential function. Oh, yes. I know what you're talking about now. Oh, right. I should be going down, I guess, because...
Or down.
Oh, this one?
It was, let's see.
Yeah, I think it's this one, because this
Yeah,
is where
yeah,
you were
yeah.
talking about
Yep.
power functions. Yeah, so it's just... Okay, if you want, you could say g of x equals this, or you could also say p of t equals p naught times a to the t. That's the other way that it's sometimes written.
Okay.
Or sometimes it's p naught times e to the kt, like
Okay.
that.
Thank you.
Yeah, no problem. Hey, so, wait. Oh, because you emailed me about being absent, right? Okay.